Imagine you're seated by the window on a long-haul flight. The engines hum steadily, the clouds stretch endlessly below, and your eyes drift toward the wing. At the very tip, you notice that familiar upward curve. It's subtle, elegant, almost artistic, but that small structure is doing something extraordinary. It's fighting invisible forces. It's reshaping airflow. It's saving fuel every single second. And without it, modern aviation would look very different. Today, we're diving deeper than ever before into the secret aerodynamics of winglets. This isn't just a surface-level explanation. This is a full exploration, from fundamental physics to cutting-edge engineering. We're going to break down the hidden physics of lift and drag, the true nature of wingtip vortices, why induced drag is unavoidable but controllable, how winglets cleverly manipulate airflow instead of resisting it, the evolution of winglet design across decades, and the future of wingtip aerodynamics. By the end of this, you won't just recognize a winglet. You'll understand exactly why it exists and why it looks the way it does. Let's begin. When most people hear the word drag, they imagine friction, air pushing against an airplane as it moves forward. And while that's part of it, drag is actually much more complex. There are multiple types of drag acting on an aircraft at any given moment. There's parasite drag, form drag, skin friction drag, and the one we care about most today, induced drag. Induced drag is unique. It doesn't come from the airplane pushing through air. It comes from the very thing that keeps the airplane in the sky, lift. Yes, the act of generating lift creates drag. This is one of the great paradoxes of flight. The stronger the lift, the stronger the induced drag. So right away, engineers are dealing with a trade-off. You need lift to fly, but lift itself creates inefficiency. And this inefficiency becomes most intense at one specific location, the wingtip. To really understand winglets, we need to go deeper into how lift actually works. A wing isn't just pushing air down, it's creating a pressure system. Above the wing, air moves faster and pressure drops. Below the wing, air moves slower and pressure increases. This pressure difference creates lift, but nature doesn't like imbalance. Air always tries to equalize pressure, and at the wingtip, it finally has a chance to do exactly that. High-pressure air from beneath the wing rushes outward, then curls upward, then spills onto the low-pressure region above. This motion creates a rotating tube of air, a vortex, and not just a small swirl, a massive, powerful, spiraling structure. These vortices trail behind the aircraft like invisible tornadoes. They persist long after the plane has passed, and they represent lost energy. Think of vortices as energy leakage. The aircraft is constantly spending energy to maintain lift. But instead of all that energy contributing to forward motion, some of it is being diverted into spinning air. That spinning motion doesn't help the aircraft. It's wasted effort. Even worse, these vortices tilt the lift vector slightly backward, which means part of the lift force is now acting against the aircraft's motion. That backward component is induced drag. So vortices don't just waste energy, they actively slow the aircraft down. And the faster or heavier the aircraft is, the stronger these vortices become. Engineers have known about wingtip vortices for over a century, so naturally, they tried to solve the problem early on. One obvious solution was simple. Make the wings longer. Longer wings reduce the strength of vortices by spreading lift over a greater distance, and this works. Gliders, for example, have extremely long wings and very high efficiency. But for commercial aircraft, longer wings create problems: increased structural stress, heavier construction, airport gate limitations, and reduced maneuverability. So while longer wings improve efficiency, they're not always practical. Engineers needed another solution, something smaller, something smarter, something more efficient. The idea of winglets wasn't new, but it took decades to fully develop. The breakthrough came when engineers realized something important. You don't need to stop vortices. You just need to control them. Instead of fighting airflow, you can guide it. Instead of eliminating vortices, you can weaken and reshape them. And that's exactly what winglets do. They act as aerodynamic tools that redirect airflow, reduce pressure differences at the tip, and convert wasted energy into useful force. This is where aerodynamics becomes less about resistance and more about cooperation with the air itself. Let's go deeper. A winglet is not just a vertical extension. It's carefully angled and shaped to interact with airflow in a precise way. When air approaches the wingtip, instead of spilling freely, it encounters the winglet. The flow is redirected upward and outward, and the strength of the vortex is reduced. But here's the fascinating part. The winglet itself generates lift. However, this lift is angled. Instead of acting purely upward, it tilts slightly forward. That forward component helps counteract induced drag. So the winglet isn't just reducing drag, it's actively producing a force that improves efficiency. This is why winglets are so powerful. They don't just block airflow, they transform it. One of the most important concepts in winglet design is something called effective wingspan. Even though the physical wing hasn't changed, aerodynamically, it behaves like a longer wing. And as we discussed earlier, longer wings mean less induced drag and better efficiency. Winglets allow aircraft to gain these benefits without increasing actual wingspan, adding excessive structural weight, or compromising airport compatibility. It's an elegant workaround, a small addition with a massive impact. Over time, engineers have refined winglet designs into several distinct types. Blended winglets, smooth, curved transitions reduce interference drag and improve airflow continuity. You'll commonly see them on aircraft like the Boeing 737 Next Generation family and the Boeing 757, where they significantly improve fuel efficiency on short and medium-haul routes. Split scimitar. Winglets. Add a downward fin to further optimize vortex behavior. A well-known example is the Boeing 737-800 and 737-900, many of which have been upgraded with split scimitar winglets as a retrofit to reduce fuel burn even further. Wingtip fences. Use vertical surfaces above and below the wing. A classic example is the Airbus A320 family, especially earlier variants, where wingtip fences are used to manage induced drag without adding excessive structural weight. Raked wingtips. Extend the wing outward instead of upward, achieving similar aerodynamic effects. This design is used on long-haul aircraft like the Boeing 787 Dreamliner and the Boeing 777, where maximizing aerodynamic efficiency over long distances is critical. Each design represents a different philosophy. Some prioritize maximum efficiency. Some balance weight and cost. Others are tailored for specific flight regimes. There is no universal solution, only optimized compromises. Winglets typically reduce fuel burn by 5 to 7%. But that number doesn't tell the full story. They also increase range, improve climb rates, reduce engine strain, and even lower carbon emissions. For airlines, this means lower operating costs, greater route flexibility, and improved environmental performance. Over millions of flights, these benefits scale enormously. Like most things, winglets are not perfect. They introduce additional weight, structural complexity, and even maintenance considerations. In some cases, the added weight can offset part of the efficiency gain. That's why winglets must be carefully designed for each aircraft. They're not just attached, they're engineered as part of the whole system. The story doesn't end here. The future of wingtip aerodynamics still has so much to offer. Engineers are exploring folding wingtips, adaptive winglets, and morphing wing structures. Future aircraft may dynamically adjust their wingtip shape during flight, optimizing efficiency in real time. The goal is the same as always: reduce drag, save energy, and improve performance. But the methods are becoming more advanced than ever. So next time you look out of an airplane window, that small curve at the tip of the wing isn't just a design detail. It's a solution to one of aviation's most fundamental challenges, a way of bending air to our advantage. A perfect example of how small innovations can unlock massive gains. If you enjoyed this deep dive, let me know what topic you want next. And until then, keep looking up. Thanks for watching. and safe travels.